3C, stationary points. Now, this table is set out very precisely, okay? Stationary points, there are two types of stationary points. We either have a stationary point of inflection or a maximum or minimum, okay? So that word turning points, that means specifically maximums or minimums, all right? That's where the function turns, it changes from increasing to decreasing. Whereas at a stationary point of inflection, it doesn't have that property, okay? Fortunately, the sign diagram of the first derivative can tell us about that. So that's what we're going to be using. Again, calculus techniques to find the stationary points. If we have this problem here, and it said find the max and min, you can graph it, okay, like I've done here, and you can just G-solve. What's the local max there? All right, G-solve, x is 0, y is minus 2. What's the local min? 2 minus 6, okay? We can do that from our calculator. We can use our calculator to check our answer. But let's look at how we can use calculus techniques to find the answer. So our first step is to find the first derivative, okay? F dash of x is going to be 3x squared times 6x. And we want to draw the sign diagram of the first derivative because it is going to tell us about the original function. If I want to draw the sign diagram, I need to know its roots. So I want to go, when is it going to equal 0? This is a quadratic. We don't have a c value, so we're just going to factorize 3x. That's common to both of these. We'll be left with x having 2. If I expand that, then I'll have what we started with. Null factor law, x is 0 or x is 2. So now we have the roots for our sign diagram. Okay, here it's going to be here. X is 0, x is 2. Now I think I've said to you guys, scale doesn't matter. Alright, but what does matter that you get the numbers around the right way. So for instance, you wouldn't write 2 and then 0, because you've written them in the wrong order. Okay? 0 is before 2. Okay, 0 and 2. Now, this is a quadratic. It opens upwards. We know it opens upwards because it has a positive a value. Alright, remember if a is positive, we're happy, we're a smiley face. And if a is negative, then it's opening downwards, it's negative. So because it opens upwards, that means it's going to be positive, then negative, then positive. Alright, so we're determining that using this algebraic process. Another way we could do that would be to graph the derivative function. Okay, so if I graph the derivative function, 3x squared take 6x, okay, you can see that quadratic. It's above, it crosses at 0, it's below, and then it's above afterwards, all right? So that's the relationship there. We can use the first derivative to support us. We can use our calculator to support us. All right, now it wants us to say what are the stationary points, okay? Stationary points occur when the first derivative is 0. So we have a stationary point at x is 0, and we have a stationary point at x is 2. We need to determine their nature. What is the nature of these stationary points? Well, what we can see is the function is positive slope. It's increasing, and then it's decreasing. We have a local max at x is 0. X is 0. What is the y value when x is 0? I'm going to put it back into the original function. When x is 0, y is minus 2. Alright, so we're getting these x values from the derivative function, we're putting them into the original function. What about when x is 2? When x is 2, we have a local minimum. Okay, it's decreasing and then increasing. Alright, negative slope and positive slope, that's our local minimum. We have a local min at x is minus 2, and we can G-solve it, or to find the y value, we can put it into the original function. Let's do that. F of minus 2. Minus 2 to the power of 3. Positive 2, sorry. 2, take 2. 8, take 6, take 2. 0. What did I do wrong? That's squared. Minus 4, take 2, minus 6. Okay, and we can see that from the graph as well. All right, if we consider the graph of the blue function, local min, x is 2, y is minus 6, local max, x is 0, y is minus 2. Okay, calculus techniques done. Okay, let's move on to B. Same deal with B. All right, I've graphed it there. We could look at the graph and we can answer these questions. I'm going to have to zoom out on the y-axis for this one. What we can see, there's a local min down there. And this coordinate here is what we call a stationary point of inflection. Okay, stationary point of inflection because it's decreasing, it goes stationary, the slope is stationary, it's horizontal, and then it keeps decreasing. All right, so that's a special point on the graph. They're the two stationary points. Let's find them using this calculus process. So, to find stationary points using the calculus process, we need to first find the first derivative. Now, what have they given us? Y or f of x? This is the wrong time. Y. They've given us y equals. So when we find the derivative, it should be in terms of y, right? Okay, in order to differentiate this, we need to use the product rule. We have one thing times another. You could expand it, but it'd take a long time to expand it. You've got a cubic, you need to expand it, and you need to distribute. It's going to take too long. Product rule. That's u, that's v. We've got x take 2. V is x plus 3 to the power of 3. Don't forget the power. That belongs to the whole term. U dash will be 1. V dash will be chain rule. 3 times x plus 3 squared. N f of x, n take 1 times f dash. Okay, we'll crank all that together to get the derivative. U dash v plus u v dash. Okay, there's our derivative function. All right, now we want to draw the sign diagram of our derivative function, don't we? Okay, again, what we could do, we could graph this function and just draw the sign diagram from the graph of it. All right, and that's going to inform us about the original function. But let's practice these algebraic techniques, okay? I'm looking along here, I want to know what are the roots? What is going to make it equal to 0? So if I'm going to solve that, I'm looking what's common, what can I factorise? X plus 3 squared is the highest common factor that exists in this term and this term. So we'll pull that out the front, which means in brackets we'll have x plus 3 plus 3 times x take 2. Okay, if you distribute this, you'll get what we have above. Alright, and I will just collect this a bit. So we're going to have x plus 3 squared. We're going to have x plus 3 plus 3x take 6. Okay, so the reason I've collected it before I've applied the null factor law is so that now we've got the first derivative in simplest form. Okay, that's the equation of the first derivative once we've simplified it. Okay, that's what it simplifies to. And now I want to know what values of x are going to make it equal to 0. And now I will apply the null factor law. Either x is minus 3, all right, and that's a double root because it touches at that point, or 4x take 3 is 0, 4x is 3, x is 3 on 4. Okay, so we're finding these points. And we can see them on the graph, right? We can see when x is minus 3, that's going to be that one there, that stationary point of inflection. And we can see down here as well, when x is 0.75, 3 divided by 4, we've got that local min, okay? So we can see them on the graph, but what we're doing at this stage is we're graphing the sign diagram of the first derivative, right? Not sure what that's doing. So if we think of the first derivative, here it is. The roots are minus 3 and 3 on 4. Okay, they're the roots. All right. Now I want to know where is it positive, where is it negative. Okay? This is a double root, which means it touches at that point. Okay. So here, if you're not really sure I might graph the derivative in a sec, but let me explain my reasoning first. This function, the second derivative, is a cubic. Okay, we have a squared times a linear. That results in the leading degree being a 3. It's a cubic, okay? Which means it has one of these two shapes, okay? A cubic either goes like this or it goes like this. All right, they're the two shapes that it takes. Now, this one occurs when A is positive, and this one occurs when A is negative, like quadratics. Now, one way you can remember that, okay, is that if you're positive, then you finish with a happy face, okay? Whereas if you're sad, then you finish with a sad face, all right? So that's one way we can remember it for cubics, which means this function, okay, when we graph it, you see it comes up, touches, goes down, and then comes back up, okay? So what that means is we've got negative, negative, positive. Okay, tricky to do that in your head, so let's do it from the graph. What's the graph of my derivative? In simplest form, we have x plus 3 squared times 4x take 3. Okay, I'm just going to focus on the one I just put in, which is the red one. Okay, you can see negative, it's below the x-axis, touches at 3, stays below the x-axis, and then passes at 0.753 on 4. Okay, so we can get that directly from the graph of the first derivative. Okay, or we can use this process. In the test, I think I said it yesterday, you're never required to draw a sign diagram manually. Okay, we're not testing you on that. That was year 11. Now you can just go straight to your calculator. All right. But what I've done here, this sort of finding the roots, you will be required to do that manually. But determining where it's negative or positive, we don't need to know that. Okay, we can just refer to our calculator. All right, what are we doing? We're finding the stationary points. So what we can see is we've got a stationary point at x is minus 3 and a stationary point at x is 3 on 4. We need to describe the nature of these stationary points. Now, because it goes negative, negative, okay, even if you don't know what the graph looks like, because it goes negative, negative, that means it's a stationary point of inflection. You can refer to your table. All right, because what's happening is it's decreasing, it's going horizontal, and then it's decreasing again. Stationary point of inflection. Stationary point of inflection at x is minus 3. Okay, and we can just g-solve the y value of the original function. That's not it. This one. When x is minus 3, what's it? 4. When x is minus 3, y is 4. Okay, so that's the stationary point of inflection. And then we're looking at the next one. We can see it's decreasing and then increasing. It's a local min. Okay, even if we don't know what the graph looks like, we know it's a local min. Negative slope, positive slope. At x is 3/4, and the y value, what's that? It's about minus 2. Okay, so we've found the stationary points, we've described their nature, we've solved this problem. Splendid. Okay, last one. F of x equals sine x. Now, with this one, like even when you're approaching one like this, we don't have a restricted domain. And what we should remember is sine x is a periodic function and it goes on forever. Okay, so that means we could find one max and one min, and they're going to repeat themselves forever in that direction, forever in this direction. And I mean, you probably get to a stage where you remember what those points are. Let's look at using those calculus techniques again. Okay, so that's the graph of sine x. That's the graph of the original function. We can see local max, local max, local max. We keep repeating so local min, local min. Okay, calculus techniques. What do we have to do? Step 1, find the first derivative. So, derivative of sine x, cos x. Step 2, draw the sign diagram of the derivative function. Let's just consider it positive for now, because we're just going to be finding really one set of local max and min, and they repeat themselves, we can just consider positive values. So for cos x, all right, that's the derivative. When does cos x equal 0? We can look at our unit circle. All right, well, we can even just think about it. Cos is the x values. They're going to equal 0 here and here. All right, pi on 2. All right, the cos value is 0, and down here, 3 pi on 2. All right, so they're our roots, aren't they? Pi on 2 and 3 pi on 2. All right. Now we can get that from our graph, can't we? Remember I said we can get that from our graph. There is a calculator hack to put the scale in terms of pi. That's going to help you get that. All right, and then you can, this is how I'm going to think about it as well. I'm going to think about it in terms of the unit circle, right? Cos is positive, all right? In this region, if we're rotating around the unit circle, in this region, cos is positive, okay? It's positive till we get to pi on 2, and then it's negative all the way until we get to 3 pi on 2, and then cos is positive again. Okay, remember, cos is the x coordinate. Here we have positive x coordinates, okay? Positive, negative between that region, and then positive. Right, so it's going on this positive, negative, positive. Okay, what we can see, we have a local max at pi on 2, local min at 3 pi on 2. Okay, so if we were to just answer this, okay, we were to just answer this. What is going to be the y value? Okay, there's two ways we can think about it. Firstly, when x is pi on 2, what is sine of pi on 2? It's going to be 1. When x is pi on 2, sine of pi on 2 is 1. The other way to think about it, all right, is for the function sine x, okay, we've found a local max. What is the amplitude of this function? It's 1. So that means the highest it goes is positive 1, the lowest it goes is negative 1. Okay, so we have local max there, local min here. Alright, we can get them from G solving. Okay. Now that would be, we've found two solutions, but remember there are an infinite amount of solutions. So in order to account for all of them, what we should add, I think, is pi on 2 plus k2 pi, where k is an integer. Now I won't put a comma there because then we're going to end up with heaps of commas in here. For all k is an integer, okay, so that upside down a, that means for all values of k, okay, plus k times 2 pi for all values of k that belong to the set of integers. Okay, it's a long complex mathematical statement. Well, we've written it down in 7 characters. Fantastic. That's the x coordinate. Okay? The y coordinate is always the same. The y coordinate for the local max is always positive 1. And then we'll just put a repeat of that here. Plus k2 pi for all k is z. And the y value of the local min is minus 1. Okay, all possible solutions. All right. So let me just talk very quickly about that one, how we can, if we have the graph of sine x, and I'm just going to zoom right in on it, okay, because if you just graph it and you go on, hang on, what's going on? There we go. Okay, if you just graph it, what you'll see is you go, oh, that root there, it's 3 point, I mean, Desmos is good because it's telling me, okay? But in your calculator, it'll just be like 3.14159. So instead, what you can do is you can change, this is a V window setting on your calculator, you can change the scale, the step. Here it's called step. You can change your scale. Its default is 1, and so what that means is each grid line is drawn at 1. You're going to change it to a multiple of pi. Pi on 4 is a good one, okay, because then what you can see, every line on your x-axis corresponds with an interval of pi. All right, and so you can see quite clearly, crosses at pi. We've got the local max at pi on 2, the local min at 3 pi on 2. You can see them from the grid lines in your calculator. So that's how we can use our calculator with those trig lines. Excellent. Let's get into 3C, see how we go with it.